This video is sponsored by the Great Courses Plus, a video-on-demand learning service featuring lectures from top professors. Warning: sulfuric acid is corrosive, ethylene glycol is poisonous, dioxane is carcinogenic. Wear gloves when handling them. This experiment also generates volatile side products. Work outside in a fume hood. Greetings, fellow nerds. Dioxane is an easy-to-make cyclic ether. Not as popular as diethyl ether, and it is somewhat more toxic and carcinogenic, but it does have its uses. And because it's easy to make, even for the amateur, we're going to make some in this video. Briefly, all we're really going to do is to take two ethylene glycol molecules and join them together. They're essentially two halves of one dioxane molecule. First, we start with 300 ml of antifreeze. Make sure the label says it's made with ethylene glycol. And get the concentrated type and not the pre-mixed version, which is water added. Now we add in 30 to 40 ml of concentrated sulfuric acid. I'm using low-grade drain cleaner acid. You can even use diluted acid as long as you add the appropriate extra amount. Any water present will be boiled off. Now around the flask we set up a distillation apparatus. Turn on the cooling water, the heating, and the stirring, and raise the temperature until the mixture starts to boil. Adjust the heating so that you get around 1 drop of distillate every 2 or 3 seconds. Going by distillate temperature is not very reliable because at the beginning of the procedure, the distillate temperature is not very stable. Water, impurities, as well as any additives in the antifreeze will start reacting first and boiling off. It's not until they're all distilled off that the distillate temperature starts to converge and the ethylene glycol starts reacting and forming our desired product. What's happening is the sulfuric acid is catalyzing the dehydration of ethylene glycol to produce dioxane and water. Both of these have lower boiling points than the reactants, and thus they distill off and drive the reaction forward. This reaction is very robust, and even using raw antifreeze with dirty sulfuric acid will work. You don't even need to distill your antifreeze first to make pure ethylene glycol. The reaction also scales well with temperature, and if you're impatient you can increase the heating to improve the rate. I'm going with this rather slow rate to minimize byproducts. But considering how cheap the starting chemicals are, I'll let you make the judgment call if you prefer speed over yield. Now you might be asking if sodium bisulfate will work as a catalyst. The motivation being it's easier to get as a pH lowering chemical for swimming pools. I actually did try it and it did work, but it required much higher temperatures and worked much slower than actual sulfuric acid. So I strongly recommend using sulfuric acid if you can. Now as the reaction progresses, it will generate a tar of byproducts. When this starts to foam excessively, you'll need to stop the reaction. You can adjust stirring and get a temporary reprieve, but eventually it'll be too much to continue. Turn off the heating and let it cool. And just so you know, you can clean out the tar with sodium hydroxide-based drain cleaner. It's nearly impossible to get out with water alone. And here is our distillate of dioxane and water. Our work is just beginning though. Most of the work is in the purification. This mixture contains numerous side products, so we need to separate them as well as get rid of the excess water. Add directly to this mixture 10 ml of sulfuric acid. This will acidify the side products and hydrolyze them for easier separation. Now set up a fractional distillation apparatus around the mixture and start distilling. One of the major side products is acetaldehyde. This was formed by the dehydration of the ethylene glycol and distills off at around 20 Celsius. You're not seeing a clean temperature plateau for the distillation because I'm just cranking the heat and blasting through it. I have no use for acetaldehyde and I'll likely be contaminated with other impurities, as well as any additives that are boiling off now as well. It's also toxic and carcinogenic, so I don't even want to keep it around. Anyway, the reason why we add sulfuric acid at the beginning is to hydrolyze another side product, 2-methyl-1,3-dioxylane. This was formed from the reaction of acetaldehyde and ethylene glycol. Under acidic conditions with lots of water, it will hydrolyze back into ethylene glycol and acetaldehyde, allowing us to remove it. You might be asking why it wasn't destroyed in the acidic conditions of the original reaction mixture. It was acidic, but it had no water as the water was constantly being boiled off as it was formed. But our distillate has lots of water, so we can destroy it here. Okay, keep distilling until you reach about 84 Celsius and then change out the receiver. You can see we have a lot of acetaldehyde and other side products, so fractional distillation is absolutely necessary for purification. Alright, dioxane and water have a low boiling azeotrope at 87 Celsius. So distill past that and change out the receiver at about 94 Celsius before stopping the distillation. The rest is mostly water and other impurities. And here's our azeotropic mixture of 17.9% water and 82.1% dioxane. Now we need to remove the rest of the water. Since this is already an azeotropic mixture, we can't use distillation. We're going to need a chemical method. Let me transfer this azeotrope to a larger container. Now we add in 40 grams of sodium hydroxide and stir. Sodium hydroxide absorbs the water and dissolves, forming a separate layer from the dioxane. You'll notice it's starting to change color. This orange stuff is actually any remaining impurities like acetaldehyde being polymerized by the sodium hydroxide. So this step not only removes water, but also the remaining impurities. It's also the reason why I'm not using a more powerful drying agent like molecular sieves. Molecular sieves only remove water, and not those other impurities. Okay, looks like there was a lot of water and the sodium hydroxide solution has dissolved. I'm going to add another 40 grams of sodium hydroxide and hope the mixture separates again. Now, potassium hydroxide is even better for this, and I recommend going with that if you can. I'm using sodium hydroxide because it's easier to get for the amateur. Okay, looks like it's separating somewhat. I'm going to let this go overnight to try and remove as much of the water and impurities as possible. Okay, here we are the next day, and we can see we have a nice and relatively clear layer of dioxane along with a gooey layer of sodium hydroxide, water, and polymerized impurities. Decant off the dioxane into a new container. A disadvantage of a gooey mixture like this is that the goo has probably absorbed a lot of dioxane in it. Potassium hydroxide would be better, as it would remain liquid, and thus you can use a separatory funnel for better separation. Now at this point, to destroy the last remaining impurities, we would use sodium metal just like we did with purifying triethylamine. But pure sodium metal is very hard to get for the amateur, so we're going to use the crude sodium mixed with magnesium oxide, made from magnesium and sodium hydroxide, as I've shown in another video. This mixture will destroy any remaining water and reactive impurities, and you can see it working from the bubbling here. I'm going to put it on stirring to smash apart the nuggets for greater activity. Now this will take some time to work, so I'm going to let it go overnight. Here we are the next day. Now we set up for distillation and simply distill over the dioxane. And there we have it, high purity dioxane. Now a special note about storage. Dioxane, like most ethers, tends to form explosive peroxides on storage with air. It's a small amount and mostly harmless because it's diluted. But if you distill or dry off the dioxane at a later date, it will concentrate in the residues and explode. This is one of the sources for that old stereotype of chemistry labs constantly exploding. It's not entirely an urban legend. So to be on the safe side, don't let the dioxane sit for more than several months. Use it up before then. Alternatively, store it over sodium metal if you have it. It can also be stored over sodium hydroxide. It'll last longer but shouldn't be ignored. I'll make a separate video on dealing with peroxides in ether solutions. Anyway, as you've seen, dioxane dissolves both water, polar, and organic substances, so it can be used for experiments requiring the combination of a diverse set of reagents. I want to use dioxane in my pyrimethamine synthesis, although I have no idea if it'll work. We'll see what happens. Thanks for watching. This video was sponsored in small part by the Great Courses Plus, an online learning service featuring thousands of videos by top university professors as well as experts in their respective fields. Subscription gives you unlimited access to a diverse set of fields from chemistry to cooking to photography. For you chemistry lovers, courses on important topics like thermodynamics are available that you won't find on my channel. It's a great source to round out your knowledge. As part of a special promotion with my channel, the Great Courses Plus is offering a free trial. You can check them out at this link, thegreatcoursesplus.com/nerdrage, or click on the link in my video description. These videos are also sponsored in large part by my patrons on Patreon. If you're not currently a patron but would like to support the continued production of science videos like this one, then check out my Patreon page here or in the video description. I really appreciate any and all support.